What's up, mathematicians? In this video, I'll be showing you an example of an indirect proof, also known as a proof by contradiction. In this particular proof, I'll show how we can prove that an irrational number plus a rational number must be irrational. So when I take the sum of an irrational and rational numbers, the resulting sum must be irrational. So let's start out by stating our given and goal. Okay, so given, I'm going to state it this way, given x is irrational, and y is rational. So given x and y such that x is irrational and y is rational, our goal, show that x plus y, the sum of x and y, is irrational. All right. So where do we start? Well, as I said, this is an indirect proof or a proof by contradiction. And the reason we call it a proof by contradiction is we're going to start out by assuming the opposite of the thing we're trying to prove. And if assuming the opposite of the thing we're trying to prove leads to a contradiction, by assuming this goal here, if we assume this is false and that leads to a contradiction, we can conclude that this in fact must be true. So we're going to start as follows. So assume that x plus y is rational. Okay, and so we're going to assume x plus y is rational, and eventually this will lead us to a contradiction, and that will lead us to conclude that x plus y is actually irrational, not rational. So let's see. Let's then say let z equal x plus y. So z is rational because we are assuming that the sum of x and y is rational, and that's z. So z is rational. Okay, so note that, let's see, x is our irrational number? Yeah. So note that y equals a plus b, and z equals, sorry, did I say a plus b? A over b, and z equals c over d, where a, b, c, and d are integers. Okay, so the reason we can conclude this is that we are assuming that z is rational, and as we have at the top, that y is rational. You see that here at the top. Okay, and we're assuming z is rational as well. And so what is the definition of a rational number? Definition is that a rational number is an integer over an integer. Integer divided by an integer. So we'll set up y and z as an integer divided by an integer. It could be any integer at all, doesn't really matter. Okay, so then we can say next that we'll replace y with a over b and z with c over d. So let's see. So z, which is c over d, is equal to x, our irrational number, plus a over b. So we've just taken this and plugged it in there, and this and plugged it in there. And that's what gives us this new equation. Well, what follows from this? Well, I can subtract c over d from both sides, and that will lead us to the following. It will lead us to saying, well, okay, oops, actually, I'm subtracting the wrong thing. Just realized because of the way I wrote this equation. I'm going to subtract a over b from both sides. So, okay, so that will lead us to the following state, that c over d minus a over b is equal to x. Now what I'm going to do is I'm going to multiply the top and bottom of the first fraction by b, and the top and bottom of the second fraction by d. So our next step is as follows. So c times b divided by b times d minus a times d over b times d. Okay, so why is this true? Well, I've just multiplied the top and bottom of this one by d, top and bottom of this one by b, so I haven't changed anything, but what I have done is got myself a common denominator on the left side of this equation. On the right side, we still have x. Okay, so now our next step is to say, that, okay, let's combine these fractions, and we get cb minus ad divided by bd is equal to x. Okay, so maybe you see where this is going, but let's review, what we've learned so far. We have a number x, and let's wait. So we're assuming that x plus y is rational, and we are also assuming at the top here that x is irrational. Let me put that in a different color because I'm going to refer to that again. So we're assuming that x is irrational, right? But also assuming that z, which is equal to x plus y, is rational. Okay. So now we go down here and we say, wait a second. This is an integer. Why is it an integer? Well, when you multiply, add, and subtract integers, you get other integers. If you divide integers, you don't necessarily get integers. But multiplying, adding, and subtracting integers just gives you other integers, like 2 times 3 minus 4, is some integer. Whenever you multiply, add, and subtract any different integers with each other, you always get more integers. And on the bottom here, we have the same thing, right? B times D is an integer if both B and D are integers. Okay, so what that means is x is equal to some integer divided by some integer. In other words, x is equal to an integer divided by an integer. Okay, so therefore, x is rational, because since it's an integer divided by an integer, it must be rational. However, at the top, we see we've assumed that x is irrational. And now here we have that x is rational. So this is a contradiction, right? Oops. Get back to where we were. So this is a contradiction. And so we'll go ahead and state that. So this contradicts our assumption that x is irrational. Therefore, and let's see how we wrote it up here. So therefore, we're trying to prove that x plus y is irrational. Okay, so therefore, x plus y must be irrational. Okay, and that's our proof, that the sum of an irrational number and a rational number must be irrational. Now, if you have your skeptic hat on right now, you might have some questions, right? Why is this a valid way to prove, something? We're not going to unpack all of that logic right now. I just wanted to show you an example of how you can use the approach, the indirect approach to proof. But that's a good question. You might also, look at the different algebraic steps and, consider definitions and all that sort of thing. So as a skeptic, there are all sorts of things you might take a closer look at. But the fact is, this is a correct proof. It is true that a rational number plus an irrational number must be irrational. And yeah, well, I hope this was helpful for you, at least understanding a little bit about the approach of an indirect proof, where you assume the negation. You assume that the thing you're trying to prove is false, and that leads you to a contradiction. And then you conclude that the thing that thing that you're trying to prove must be true. All right, so I hope to see you in future videos about proofs and other things.